So this is basically the pre-lab for lab 3, and it's also an introduction to reaction rates. What that tells us about mechanism. So first of all, we talked about this in class last week. So if we have a reagent going to product, and it's a single step, it's an elementary step, you can plot this as an energy diagram. Some reaction coordinate, usually a bond length, something like that. We have the reactant going to product. We have a thermodynamic quantity, which is delta G of the reaction. The Gibbs free energy of the reaction is just the difference in energy between the reactants and the products. And we can't really change that. The molecules have their intrinsic energy. We also have an energy of activation of some sort. This is where kinetics comes in. So this is how fast the reaction will happen. How many of these R molecules are going to have enough energy to get over this reaction barrier and get over the products? And that will vary reaction to reaction. So the reaction rate is always going to be the change in concentration of either the reagents or the products. You can look at either one over time. So delta concentration, delta time. You can actually make this dx dt into integration. We'll look at integrated rate laws here in a bit. I promise you guys this wouldn't be a math class, so that we won't actually do integration. The rate for an elementary step, again, any single step, any step where bonds are made and broken simultaneously, is going to be equal to some reaction rate constant, lowercase k, for that step, times the concentration of whatever reagents are there. If there's 3 reagents, it's 3 reactants. It's 2, it's 2, it's 1, it's 1. This looks like the overall rate constant, or rate equation. The overall rate equation is some combination of the rate equations for the elementary steps. More on that in a minute. Here I've drawn a pretty simple acid-base reaction, acetic acid reacting with hydroxide to give acetate and water. As we're looking at in class, you can look at the stabilities, the acidities of the acid and the conjugate acid, in this case acetic acid and water. Water has a pK of 14, acetic acid has a pK of 4.5. The weaker acid is favored, right? So acetate and water are favored here. And you can actually calculate the equilibrium constant using the pK values. pK values are log values, so the equilibrium constant winds up being 10 to the 14th divided by 10 to the 4.5. All right? The rate of this reaction, it's a single reaction, right? This hydroxide is going to grab the proton, take some electrons out of the hydroxide. This happens at one time. So it's an elementary step. The rate is going to be the reaction rate constant times the concentration of acetic acid times the concentration of hydroxide. Right? These molecules have to bang into each other. The more of one of them there are, the faster the other molecule is going to bang into a reagent. And this reaction rate constant for Bronsted acid-base transfer, proton transfer, is what we call diffusion control. It's basically if an acid and a base collide, the proton gets transferred if it's thermodynamically favorable. So you'd have a diagram like this. Reactant's quite a bit less stable than the products, and a really low barrier of activation. So this reaction will be very fast. In the lab, we're going to look at a substitution reaction. So I'll draw the actual reaction here in a minute. Make sure my pen doesn't dry up. Let me see if that's visible. Okay, so in a substitution reaction, one group, in this case Y, substitutes for another group in a molecule, X. Okay, so staying really vague and generic. Y is going to substitute for X. We're going to go from Rx plus Y to Ry plus X. And there's 3 different ways you can imagine this happening. So Y could directly substitute for X. Here I'm showing Y as having electrons, so it's a Lewis base. So Y would give its electrons to R. X would take the electrons and leave. We'd get our Ry. We'd get X minus. And the rate for this, if this happens at once, it's an elementary step, so the rate's going to be K times the concentration of Rx times the concentration of Y. Second possibility is that X simply takes its electrons and goes. Right? This would give a positively charged R, which Y with its electrons could then attack, make a bond to. We'd get Ry plus X again. But you might imagine, right, so something negative reacting with something positive, that's probably going to happen really fast. So this is going to be a fast step. Rx going to R plus and X minus, where a bond simply breaks, you might imagine that's slow. In this case, the rule is nothing that appears after the rate limiting step appears in the overall rate equation. So the rate equation for this reaction would be K times the concentration of Rx, right? So this is the slow step. This is the rate limiting step. You've probably heard of that. So if this is the rate limiting step, and Y doesn't appear in the rate limiting step, it only comes in after, it really doesn't matter how much Y we have, that the rate goes at the rate it goes, only based on how much Rx is there. And we'll see examples of this type of chemistry as well. The third possibility doesn't actually pertain to chemistry in this chapter with alkyl halides. So you could imagine that the nucleophile attacks the electrophile. Here I'm using words you don't know yet. You'll see them in class soon. So the molecule with electrons, the Lewis base, Y minus, attacks the Rx molecule and makes a bond. And so now we have Y and R and X all in one molecule. And then X could leave, and give us our RY plus X. This is an addition elimination mechanism, and there are also examples of this in organic chemistry, a lot in inorganic chemistry, but we're not going to see that today. In this, again, the rate would depend on which step was slow, although both reagents appear in the first step, so they probably both appear in the overall rate equation. Okay, so again, an elementary step is going to have a rate equation, and the overall rate, or the overall reaction will have a rate equation. And so the two mechanistic possibilities that we're going to consider in today's and this week's lab are over there. I should have mentioned, you can obviously pause this at any point, replay it. You can't do that in class so well. So hopefully this works out. Okay, so some background on kinetics. We will refer to reaction rates as some sort of order, depending on how many reactants appear in the rate equation. So a zero order reaction, the rate is simply equal to the rate constant, K. And that's pretty rare. You're not going to see a zero order reaction in organic chemistry. An example of that would be radioactivity. There's basically just a reaction. First order reactants, or a first order reaction, the rate is equal to a reaction rate constant times the concentration of one reagent to the single power. A second order, the rate is equal to a rate constant times the concentration of R squared, or two different reagents, A and B, say, so K times the concentration of A times the concentration of B. And you can imagine that if you analyze the data, these will all give you different appearances. We'll talk about that in just a second. So, but basically, the first order reaction, in a zero order reaction, if you double the concentration of a reagent, nothing happens. In a first order reaction, if I double the concentration of the reagent, the reaction rate goes up by a factor of 2. In a second order reaction, I erased my 2 here. In a second order reaction, if you double the concentration of the reagent, the reaction rate goes up by 4, goes up as a square. And then in a reaction like this, where the rate is equal to K times A times B, if you double A, the rate doubles. If you double B, the rate doubles. If you double both of them, the rate goes up by a factor of 4. You can also do something, you can run reactions that are what are called pseudo first order kinetics. So again, let's say we have a reaction A plus B goes to C plus D. The reaction rate is K times the concentration of A times the concentration of B. And again, K is going to be unique to the particular reaction. Well, we can set the concentration of one of the reagents, let's say B, as being very much greater than the concentration of A. So that what we actually see is basically that the rate equals some pseudo first order rate constant times the concentration of A. And that pseudo first order rate constant is going to be the actual reaction rate constant times the concentration of B. But because B is there's so much more B than A, the concentration of B is essentially constant. So let's say B is 10 molar and A is 0.001 molar, right? If all of A reacts, the concentration of B is still basically 10 molar. And so the reaction rate doesn't really change over time. Like I said earlier, I alluded to this, we can integrate the reaction rate equations because they're essentially differential equations. So So it's in a zero order, and what we do when we integrate it, we can linearize, we can come up with a linear expression that involves the rate constant. So in a zero order rate constant, or a zero order reaction, if you plot, well, forget about plots for a second. When you integrate, you come up with a natural log concentration of A at time t. So that's concentration of A at time t is equal to minus kT, whatever the time is, plus the natural log A 0. Concentration of A 0 is the initial concentration of A. In a first order reaction, if you plot, again, forget the plots, that 1 over the reciprocal of the concentration of A at time t is equal to kT plus the reciprocal of the initial concentration of A. In a second order reaction, the concentration of A at time t is equal to minus kT plus the initial concentration of A. So these all, I keep saying this, they're all linear expressions, right, where the slope is k. So if we were to plot for a first order reaction, you can pause it and read this down here. For a first order reaction, if we plot the reciprocal of the concentration of A at time t versus time, then the slope is k, and the intercept is the reciprocal of the initial concentration. Okay, so which plot gives you a linear, which variables you plot to get a linear line? Sorry, that's not very smooth. But if you plot AT versus time and get a linear plot, then it's a zero order reaction. If you plot the reciprocal of the concentration of A at time t versus time and get a linear plot, that's going to be a first order reaction. And if you plot the natural log of A at time t versus time and get a linear plot, it's a second order reaction. And again, if you're running under pseudo first order kinetics, it's going to look like a first order reaction, as long as you use the reagent that's in lower amount. Okay, so that brings us to initial rates. The rate, if you look at these rate equations, right, is if A plus B goes to C plus D and the rate is K times A times B, right, well, halfway through the reaction, you've got a lot less A and B, so the reaction rate's going to slow. So almost every reaction, the reaction rate slows as the reaction proceeds because the concentration of reactants falls. And this ignores the complication of equilibrium. So in most reactions, you do have some sort of equilibrium where the back reaction can become important. But we're going to ignore that for now, and we'll ignore it in today's reaction for a variety of reasons. So the initial rate usually gives us the best information about K, the reaction rate, and the actual rate, right? The actual rate, the rate of the reaction is a change in concentration over time. Okay, so forget the equation. That's the rate. That's what we can measure. You can go in, and in this week's lab, we're going to use NMR to measure the concentration of reactants and products. And so you can measure the actual rate. So like I said, if you have A plus B goes to C plus D, you might have a rate that's equal to Ka, K times the concentration of A, or K times the concentration of A times the concentration of B. Right? On the left, if you double the concentration of A, the reaction rate doubles. If you double the concentration of B, really if you make any change in the concentration of B, nothing happens because B doesn't appear in the rate equation. So you could run a reaction with the concentration of A equal to 1, measure the initial rate, double it to the concentration of 2, measure the initial rate. The second initial rate should be twice as high as the first initial rate. You could cut the initial rate in half of A, the initial rate should fall by half. On the other hand, if you have a second order reaction where the reaction rate is equal to K times the concentration of A times the concentration of B, if you double the concentration of either reagent, the reaction rate doubles. If you double the concentration of both reagents, the reaction rate goes up by 4. And so I should say that reaction rate is going to be equal to the initial rate. That's what we're talking about is going to fall. Because like I said, later toward the end of the reaction, you don't really know what the concentrations are that well. So that's today's lab, or this week's lab. You can pause this here. I'm going to start erasing. So in this week's lab, we're going to substitute iodide for bromine. several reactions. I'm going to give you one example. I'm going to try to use a piece of pen to do it. All right, we're going to substitute I minus for Br minus. We'll talk more about this in class, but basically if you see any of the group 1 metals, lithium, sodium, potassium, you should always assume that they're ionic. They basically only make ionic bonds. So this is sodium I minus. We can essentially ignore the sodium in this reaction. It's what's called a spectator ion, right? It actually does play a role, but not a big one. And so we've got starting materials, and so the question is this what's the order of this reaction? There are two possibilities. Well, there are three possibilities, I guess. The rate could either be equal to the reaction rate constant times the concentration of butyl bromide. Could be equal to the rate constant times the concentration of sodium iodide, or it could be equal to the rate constant times the concentration of butyl bromide and sodium iodide. And you're going to measure this. You're going to use NMR to figure this out. So we're going to do this reaction at different concentrations of the two reagents, and then look at how the reaction rate changes. So you're going to do, for each reaction, for each of the reactions that we do in the lab, we're going to do these three plots. Concentration versus time, reciprocal concentration versus time, natural log of concentration versus time. We're going to see which one is linear. And then we're also going to, for the first 2 to 4 time points, we're going to plot we're going to plot the concentration of A versus time. That is the rate of the reaction. This is for the initial rate. We're going to do the first 2 or 4 because that's initial. And so the way this reaction is going to work is we're going to mix our reagents. I have no idea if I'm on camera or not. We're going to mix our reagents, and then we're going to immediately we're going to mix the reagents in an NMR tube. We're going to immediately put the NMR tube in the NMR spectrometer. We're going to follow the reaction by NMR. Right, so which of the resonances, the question here is, which proton should you follow? We're going to monitor this reaction by NMR. So we could look at the methyl protons. We could look at the next CH2 protons, we could look at the middle CH2 protons, or we could look at the CH2 protons bonded to the hetero atom. Think about that. We'll talk about it when you come to lab. We can't really follow sodium iodide or sodium bromide by proton NMR because there are no protons. All right, so this is going to be a lot of Excel data. You're going to come to the lab at the assigned time. You're going to run an assigned